Relationships in tables yesterday, and in those tables we were looking at trying to find a way to determine whether or not the relationship was proportional, and we decided if there was a constant of proportionality, then it was a proportional relationship, and if there wasn't, then it wasn't a proportional relationship. So we're going to look at proportional relationships and equations today to try to find a similar way to determine whether or not they are proportional. But to start things off, we have a little activity here where there are three different rectangles, and we could call this one rectangle number 1, we could call this rectangle number 2, and this is rectangle number 3. Now if we look at these three rectangles, I want you guys to describe any patterns that you see as it goes from 1 to 2 to 3. Obviously they're getting bigger, but how are they getting bigger? Try to describe the pattern with which they get bigger. And then what predictions can you make about future rectangles in the set if your pattern continues? So for example, if I were to say, what is the 50th one in this series going to look like? What kind of information would you be able to provide me in order to tell me what that 50th one is going to look like based on what patterns you see here? Okay, so I'll give you guys about a minute. Just try to describe the pattern, describe anything you see that explains how these rectangles are getting bigger every time.
How they're correlated.
So you might want to look at things like the height and the base. How are they changing? You might want to look at things like the area. How is the area changing? Look at the ratios of the height and width.
Give me a random number.
57. Okay, I want to hear from Richter. What did you notice when you looked at these rectangles? What did you notice? What's a pattern that you observed?
You add 3 more lengths.
Oh, okay, yeah. So if we look at the length, so you're talking about this part right here, right?
Yeah.
So Richter was looking at that and he said it was 3 here, and then it was 1, 2, 3, 4, 5, 6 here. Okay, and then it was 1, 2, 3, 4, 5, 6, 7, 8, 9 here. All right, so it looks like it's adding 3 every time to that length or to the base. What else did you notice, Riley?
Like the area of each is a multiple of 3.
Oh, the area of each is a multiple of 3. Okay, so the area of this first one is just 3. The area of this next one would be 1, 2, 3, 4, 5, 6, 12. Okay, the area of this one would be a 3 by 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 times 9 is 18. Okay, so the area is increasing, and every area is divisible by 3. So that's interesting. What else did you notice, Emma?
The height is going up by 1 every time.
Okay, yeah, so the other side of the rectangle, the short side is 1, and then it's 2, and then it's 3. So yeah, it's going up by 1 as well. What else? Any other things you guys noticed? How about the relationship between the number in the series? So I would call this one the first one, and then the height. So do you guys notice that? The first one has a height of 1. The second one has a height of 2. The third one has a height of 3. Nora, what did you notice?
So number 1 has the height of 1.
Yep.
And it's pretty much the same number.
Same number, yeah, I noticed that as well. And then what's the relationship between the number the number in the series and the base? What do you guys notice there? What is it, Nora?
Multiplied by 3.
It's multiplied by 3, exactly. The first one has a base of 3. The second one has a base of 6. And the third one has a base of 9. So let me ask you this. If I wanted to know what was the 50th in the series, if this pattern kept going all the way to number 50, what would that rectangle look like, okay? So the 50th, I'm going to draw a little representation of that rectangle. The 50th in the series, how would I know what to draw? Obviously, this is going to be much smaller than what it's going to look like. But Cloud, how would you describe it?
It's gonna have a width of 150.
Okay, yeah, so we know, take that same pattern, it's the number 50, so we multiply that by 3, so the base would be 150 units. And what would the height be? Angela, do you know?
No, there's just people.
Oh yeah, they can wait, they'll be fine. What'd you notice, Maddie, Vollendorf?
Oh, the height of 50 will be 50.
Yeah, exactly. So we know exactly what this one would look like based on the pattern that we saw previously. Nice, okay, good. All right, so let's continue on to the next part of this lesson. So the next part is going to be looking at converting more conversions, okay? So we talked about conversions a couple lessons ago when we were looking at converting between meters, centimeters, and millimeters. But this one we're going to convert between Fahrenheit and Celsius. Now I think this is a really interesting one because a lot of people think, well, does anyone know what is the temperature of water freezes? What is it?
32.
32 degrees Fahrenheit, right? Now, it's also 0 degrees Celsius. So a lot of people think, oh, well, if I have Celsius, I just add 32 degrees, and that's how I find Fahrenheit. But it actually doesn't work like that. It works like this. We use this equation to be able to convert between Fahrenheit and Celsius, okay? So whenever you are given a temperature in Celsius, you have to multiply it by 9/5 and then add 32. So that number 9/5 is kind of hard to work with. So I'm going to rewrite this equation. Instead of 9/5, I'm going to use a decimal. Does anyone remember how do I turn 9/5 into a decimal? It's a decimal equivalent. It's the same process when we take when I give you your quiz back and it says 8 out of 10. You have to turn it into a decimal first before converting into a percent. What do we do, Eden?
Divide 5 by 9.
Close, but we actually reverse that. So we do the top divided by the bottom. So I'm going to do 9 divided by 5. Oops. 9 divided by 5. And I get 1.8. Okay, so I'm going to rewrite this equation so it'll make more sense. It's going to be over here. Let me zoom out and say that Fahrenheit, degrees in Fahrenheit is found by taking 1.8, multiplying that by Celsius, and then adding 32. Okay, so that's the formula we have to use to convert Celsius to Fahrenheit. All right, so I'm going to do the first one for you, and then I'll let you guys do the rest on your own. So the first one, if I have the temperature of 20 degrees Celsius, I have to plug that in for C here, okay? So it's now going to become 1.8 times 20, and then I'm going to add 32 to that. Okay, so then and again, you guys can use calculators for this. 1.8 times 20 is equal to 36 plus 32. 36 plus 32 equals 68. So that tells me that the temperature in Celsius is 20. Then the equivalent temperature in Fahrenheit is going to be 68 degrees. All right. Now I want you guys to finish the rest of that table. And then when you're done with that one, number 2 is a little bit easier. You just use this equation here to convert between N, which is inches, and C, which is centimeters. Okay, so on your own, I want you guys to answer number 1 and number 2. Go get a calculator if you need one. Fill in the tables, and then we'll talk about which one is a proportional relationship afterwards. Okay, ready, set, go. Oh my goodness. What's up? No, you gotta take 4 and multiply it by 9/5, which I converted to 1.8. So 4 times 1.8. And then you have to, no, you gotta do 4 times 1, okay, and then you have to add 32. Okay, so write that down. But I think we did something wrong there. Let's see. Yeah, so look at this. So you have to take the temperature and multiply by 9/5. Now, we're not gonna use 9/5 anymore, we're gonna use the conversion. It's not 9/5, it's 1.8. So you can do 1.8 times the temperature, which is 4. 4 times 1.8. 7.2. To that, we have to add 32, which is 39.2. So that's the temperature in Fahrenheit. Okay, go on to number 2. I disagree with this one. Remember, you take the temperature in Fahrenheit, multiply it by 9/5, and then add 32. I just showed you up there, were you not paying attention? What do I have up there for my converted equation? F equals what? Yeah, so 1.8 is 9/5 as a decimal. Hey, use a calculator, don't use your phone. Put that away. Use your calculator. Yes, exactly. Oh, not for this one. This one's using this equation. Different equation. There's a different equation for number 2. I mean, I have calculators over here. 2.54. Yes, look at this. It says N is inches. Nope, you just use that that other equation. So guys, on number 2, use that other equation. The equation for number 2 is different. You're not adding anything. On that second equation, you're just taking inches and multiplying by 2.54. Yes.
Doing this right here, Richard. Okay. Again, P is packets, B is bytes, right? So you just, so B would be 30,000, so it'd be 30,000 is equal to 1,500 times some unknown number. So just plug the numbers into the formula.
Okay, let's go through these answers here. So if I have a 4 degrees Celsius temperature and I convert it to Fahrenheit, what is that going to be, Stice? 4 degrees in Celsius, what is that in Fahrenheit? It's going to be what?
108.
I disagree. How'd you find 108?
Isn't it 4 times 1.8? And then I just
And then you gotta add 32. Yeah, so I think it's a little bit less than that. JJ, what'd you get? If it's 4 degrees Celsius, what is it in Fahrenheit?
I got 43.2.
Still wrong. Okay, let's hear from Angel. What'd you get?
I got 37.8.
Still wrong. Okay, let's hear from Nora.
39.2.
Yeah, guys, all we have to do is plug this number into the formula, okay? So we just take 4 times 1.8, because 1.8 is the same thing as 9/5. Okay, so we do 4 times 1.8, okay, equals 7.2. And then all we have to do is add 32 plus 32. Okay, it's 39.2. Yeah, that is an addition sign, not a multiplication sign. So 39.2 is the temperature in Fahrenheit that is the same as 4 degrees Celsius. All right. Now, Burke, what about if the temperature was 175 degrees Celsius?
347 degrees Fahrenheit.
Yeah, nice. 347 degrees Fahrenheit. Good job. Okay, so now let's go to number 2. For number 2, all we have to do is use this formula. It's a lot more simplified. N is the length in inches. We multiply that by 2.54 to find the length in centimeters. So Jocelyn, if it's 10 inches, how many centimeters is that going to be? Okay, Anna, if it's 10 inches, how many centimeters is that going to be?
25.4.
Yeah, it's 25.4. Okay, all we have to do is take the inches, multiply it by 2.54, because that's what the equation tells us to do. It's 2.54 times n, and n in this situation represents any length in inches. All right, so if we have 8 inches, how many centimeters is that going to be, Eden? 20.32, exactly. We do the exact same thing. So you take 8, multiply it by 2.54, okay, and that equals 20.32. 20.32. All right, now what if we have 3.5 inches, Angela? How many centimeters is that going to be?
I didn't get to that.
Okay. Sienna, how many centimeters is 3.5 inches going to be?
8.89.
8.89, exactly. 8.89. Okay, so let's take a look at this second table here. When we convert from inches to centimeters, is there a constant of proportionality, Riley?
Yes.
Yes, there is. There is the one single number that we multiply inches by to get to centimeters. What is the constant of proportionality on this one? Maddie Vollendorf?
Times 2.54.
Exactly. So, because there is a constant of proportionality, that means that this is a proportional relationship. So I would say that this is a proportional relationship. Okay? And check this out, guys. When I look at just the formula itself, I'm going to zoom in on this formula. It's very important. When I look at this equation, I can tell just by looking at the equation that this is a proportional relationship because I have one single number being multiplied by inches to get to centimeters. And because there's one single number being multiplied by inches to get to centimeters, that right there tells me that this is a proportional relationship. Now let's compare that to this formula. This formula is a lot more complex. We have to take degrees in Celsius and multiply it by 9/5 and then add 32. So right there, because I'm adding 32, because of this fact right here, that tells me that this is not a proportional relationship, okay? Proportional relationships have in their equations one number being multiplied by a letter to find another letter or a variable. All right, let's go on to the next page. Next page is talking about cubes. So we need to review cubes. What do we know about cubes, like these things? Raise your hand if you have something you can contribute to the discussion of what cubes are. No?
Oh, I have one.
Okay, Nora, what do you know about cubes?
So cubes, they have a square and are 6 sides.
Nice, good job. Yeah, so every cube, if I look at this big one here, okay, I know that this is 1 square. There's another square over here that's 2, 3. There's one on the bottom, that's 4. There's one on the back side, that's 5. And there's one on this left side we can't see over here, it's 6. So there are 6 faces on every cube. Okay, what else do we know about cubes? Anything else? Riley?
It's a 3D square.
It's three-dimensional, right? So we have a length, a width, and a height to this cube. Okay, what else do we know? Anything else? Nora?
It's a shape.
It is a shape, yeah. It's a shape. It's specifically a three-dimensional shape. I want to know how many edges. So if this right here, let's take this middle one. That's 1 edge right there. That's 5. How many total edges are there? What do you think? Angela, how many edges?
8.
There are more than 8 edges. How many total edges are there? Riley?
12.
There are 12 edges, yes. 12 edges. All right, so we want to fill in these first 2 tables. We're going to ignore the one on the next page that's volume right now. So here's how I need everyone's eyes up on the board, because I'm going to show you exactly how to find the total edge length on a cube. So Gregory, this is the board I'm talking about. Yeah, thank you. All right, so Catherine, you want to take a look at this? And Shane? Thank you. So to find total edge length, we need to take the side length. So take this one in the middle, for example. One side is 5. And that means every other single side is 5. Every single edge is 5 units on this one, okay? Now, there are 12 edges, and every single edge is 5 units. So how am I going to figure out what the total edge length is? Angel?
12 times 5.
12 times 5, exactly. So I just take the side length, whatever it is, whether it be 3, 5, 9.5, S, doesn't matter. We'll do the 5 one. If the side length is 5, I just multiply that by the number of edges, which is 12. So what's the total edge length if the side length is 5? 60. It's 60, exactly. Okay, so that one's really easy. Just take the side length and multiply it by the number of sides, number of edges. All right, now surface area is a little bit different. Surface area is the area of every single face added together. Okay, so if I was going to find the area of this square that I'm outlining right here, so if you're not looking at the board, you won't know what I'm talking about. This square that I'm outlining right here, I want to know, how am I going to find the area of that square? Angelina's not here. Someone raise their hand. What do you think? Find the area of that square I just outlined. Area of this square right here. Maddie Vollendorf, how do I find the area of a square? 5 times 5, exactly, because I know every side is 5 units. So to find the area of a square, it's length times width, or 5 times 5. So the area of that face right there is 25 square units. Now, how many faces are there on a cube again, Burke?
There is 6.
There's 6. And every face is going to be the exact same. And if the area of one of the faces is 25, then Catherine, what do I need to do to find the area of all the faces put together?
You can do 25 times 6.
Yeah, exactly. 25 times 6. So to go back and show you guys what I did here, side length is 5. I need to multiply that by 5 again because every side is 5. And that's 25. And then I need to multiply that by 6 because there's 6 faces. And when I multiply 5 times 5 times 6, I get 150 square units. Okay, so I did the first for you guys. Now I want you guys on your own to fill in the rest of these tables. Okay, ready, set, go. So again, be careful when you're finding surface area. You got to find the area of one face first, and then multiply it by all the faces, by 6, because there are 6 faces. For some reason, that's enjoyable. I've been doing that a lot. Feels good. Here's your good shot.
Yeah, pass it over here.
What are we doing?
Only if you're done do you get to play with the pencil.
I'm done, I got it for free.
What you saw me do?
Finish these? Let's see here. Nice, good work. Nope. Okay, which one is a proportional relationship? Oh, no, you did these wrong. Okay, I showed you this one, you still got it wrong. You gotta find the area of one side and then multiply it by 6 to find the area of all sides put together. Okay, you find the area of one side and then multiply it by 6. So for like this one right here, the area of one side would be 3 times 3. But no. 150 is just only with that one. Now we're talking about a completely different cube. Side length is 3, so we have to find the area of that one side. That's 3 times 3, which is 9. So the area of one face is 9, and then there are 6 faces. We'll be in elementary.
Wait, what's S?
1 for 9.5 is still wrong.
What does S mean?
S is just any side length, so that's why we're going to start making an equation.
114 times that.
No, so what do we do to side length to find total edge length? Multiply by what?
Multiply these by 12.
Exactly, so this one would just be 12s. Because you're multiplying the side, whatever it is, times 12. There you go. And what are we doing on this one?
Wait, what's 5 and 6? 30.
It's not 30s, because that's not what we're doing for every one.
We drew the 10 over there.
Well, you gotta do the same, so you gotta find the area of the face. First of all, so for this one, you gotta find the area of that face, which is 3 times 3. And then multiply by the number of faces, which is 6. Yeah. Nope. I have my own, thank you though. Okay. Gregory, please tell me if the side length is 3, what do I need to do to find the total edge length?
By 12.
Multiply it by 12, good. So what is 3 times 12, Greg? 12, 24, 36, nice. Okay, if the side length is 9.5, then Eden, what is the total edge length going to be? 9.5.
114.
Yes, 114. Okay, now if I have S was any side, then Angela, what do I have to do to the side length to find total edge length? So Angela, what am I doing to get from side? Yeah, you're multiplying by 12, exactly. So this one would be 12 times S is how I find the total side length. S is just the side length. The total edge length would be the number of edges multiplied by S. Okay, now surface area is a little bit different. So if I have the side length of 3, then Vollendorf, what is the surface area going to be? 54, good. Okay, now if the side length is 9.5, then Angel, what is the surface area going to be? No, not quite. What is it going to be, Maddie Stice?
It'd be 541.
541.6 is what I got.
Oh, I don't. My calculator was 5. Yeah, same.
Might be 5.
541.5, so somewhere in there. Okay, so in other words, now we need to come up with a cloud. Pay attention, please.
He's writing stuff on my paper.
Shh, Cloud, listen to the teacher.
All right, so now we need to know, if I'm given a side length, what do I have to do to that side length to find surface area? So just like this one over here, if I was given a side length here, all I had to do is multiply by 12, but what do I have to do to the side length here in order to find the surface area? What do I do, JJ?
Multiply it by 44. What?
Not quite. I mean, because I don't think 3 times 44 is 54. So what am I doing to get from side length to surface area? What do I have to do? What did I do here? Someone describe that process? Yeah, what did I do there, Cloud?
You multiply the side length by 5 by 6.
Yeah, but I only did that here because the side length is 5, and I have to multiply the side length by itself. So really I would say side length times side length times 6 because there's 6 faces. Now, I can rewrite this a different way. If I have a side length times a side length, anything times itself would just be that number squared, right? If I wanted to say 7 times 7, I could write 7 squared, or 7 to the second power. So here I'm going to write side length squared times 6. So I'm going to say 6 times side length squared. Now, here's the last thing I want to show you guys before we run out of time here. So I need everyone's eyes on the board. Very important. This is like the biggest takeaway of the day. Angel, everyone. All right. So if I was going to write an equation, I would say that first, if I'm given the side length, it would be 6 times the side length squared is equal to the surface area. All right. Now, if I was going to write an equation for this one, I would say that the 12 times the side length is equal to the total edge length. All right. Now, when I look at these two equations, one of them is a proportional relationship and one of them is not. Can someone identify which one is a proportional relationship? What do you think, Maddie Vollendorf?
Both times that.
Yeah, exactly, because I am taking the side length, which is one variable, and multiplying it by a single number. That's our constant of proportionality. There is no constant of proportionality here because I have to take the side length, multiply it by itself, and then by 6. So not proportional, proportional. Okay, so make sure you guys do your homework tonight. It's lesson 8 practice problems number 1 and number 4. Let's start cleaning up.